Hello and welcome to this episode of Kaggle Tutorials. This episode is part of a larger series where we will be teaching you how to build different kinds of projects as well as helping you learn different data science concepts using publicly available Kaggle notebooks as a reference. So today we're performing face mask detection. Indicated by the project name itself, the overarching objective of this tutorial is pretty simple. Given an input image, a face mask detection model that we will build should be able to detect if a person is wearing a face mask or not with a good amount of accuracy. And thanks to Ayushi Mishra for publishing the original version of this notebook on Kaggle. We'll be linking out her original notebook in the video description, so please make sure to check it out. Now let's start with the overview of the project. The project tutorial is broken down into three major parts. Part 1 will be creating a training dataset. Here, we should be able to create a training dataset of face images with proper bounding boxes of human faces and annotations, indicating whether the person is wearing a face mask or not. In Part 2, we'll move on to training an image classification model. So here, we should be able to create an image classification model like a convolutional neural network for face mask detection. The accuracy of detection will heavily rely on the type and quality of model we will be building. And finally, in Part 3, we'll be making predictions from the model. Here, we should be able to detect faces on images and make predictions on whether or not the person is wearing a face mask using our trained image classification model. Okay, now that we're done with the overview, let's start off this project by importing the necessary libraries. And here you can see a bunch of libraries that we will be using for this project. So let us go over them one by one. We'll be importing NumPy as NP in order to work with multidimensional arrays. We'll be importing pandas as PD to work with data frames. We'll be importing the OS library to work with operating system dependent functionalities. We'll be importing Matplotlib's PyPlot module as well as patches as PLT and patches respectively for plotting. We'll also be importing CV2, which is OpenCV for reading in images and performing image manipulation. We'll also be importing the label encoder from the sklearn.preprocessing module. And for tensor-based operations, we'll be importing the two categorical and normalize methods from tensorflow.keras.utils. So all of these libraries and modules are used mostly for data preprocessing and for creating our training dataset in Part 1. Then for machine learning, we'll be importing different layers, models and optimizers from the tensorflow.keras module in order to build our model. And here you can see the layers that we will use, the model that we will use and the optimizer that we will use. And finally, when we're actually working on Part 3, where we're detecting a face from an input image, we'll be using the MTCNN architecture or the MTCNN library. So here I'm importing that. We'll talk about it more when we get to that part. So I'll import all of these libraries for now. That's done. Now it's time to start creating our training dataset. So in this part, we'll be creating a training dataset for training an image classification model. The dataset for this tutorial is publicly available on Kaggle, and you can download the dataset from the given link, which I'll link out in the video description, as well as the text-based explanation as well. So once you download it, please make sure to keep the data files in the data directory of this project. There are multiple files in the dataset, however, we only need the files from train.csv and from this long file path, which is medical mask images folder for this project. So let us start by looking at train.csv. The train.csv file contains information about images such as the image name, coordinates for bounding boxes of faces, as well as the class name for each bounding box. So here you can see what a sample bounding box looks on a person's face in an image. If you're not familiar with bounding boxes, you can think of it as a rectangle that crops out the part of the image where the actual object, and in this case the face, is present. So this bounding box is bounding the face in the image. Now let us start by reading in the train.csv file from the data folder. So for this, we're using the readCSV method from the pandas library, and once the data frame has been read in, we're assigning it to the variable train. And using the head method from the train data frame, we can actually see the first 5 rows. So I'll run both of these lines. And this is our train.csv. So here you can see that we have a name column where the actual names of the images are present. Then we have the coordinates for the bounding box. We'll discuss more about how these coordinates are laid out later down this video. And we also have the class name associated with each of the images bounding box. So image 2756 has one bounding box with a class name face with mask. It also has another bounding box. That means there are two different faces in the same image. So there's another class name for that bounding box. And as you can see, there are other bounding box in the image 2756. So there are in total 4 different bounding boxes with different class names. So the data dictionary is name is our image file name, x1, x2, y1, y2 are our bounding box coordinates, and class name is our bounding box label. Now let us see the total number of rows in our data frame by calling the len method and passing in our data frame as an argument. I'm just using an f string over here in order to print the content of this function. So if I run this, we can see that the total number of rows are 15,412. Now let us also see how many unique image names are there in the data frame. Here I'm selecting the name column from the trained dataset and I'm calling the unique method off of it in order to get an array of all the unique image names in the name column. Then I'm passing the returned array inside of the len function, which gives us the count of unique elements in the array. So if I run this, you can see that out of the 15,412 rows of data that we have, there are only 4,326 images that are actually unique. So now we'll filter this dataset down in order to get all the images with class name as either face with mask or face no mask in the dataset, since classifying these labels is our primary objective for this project. Here I'm selecting the class name column from the trained dataset and I'm calling the unique method off of it. So if I run this, we get an array of all of the unique values in the class name column. You can see that there are multiple class names in this dataset. Let us filter only the class names that we want, which is face with mask and face no mask. For that, I'm initializing a list with the values face with mask and face no mask, and I'm assigning it to the variable options. Then I'm selecting the class name column from the trained data frame. Then I'm calling the isin method and passing in our list. So this gives us a boolean series where if the class name is either face with mask or face no mask, then the value is set as true, else false. So since this is a boolean series, we can filter our trained data frame using it. By using the square brackets in front of the data frame name, we're selecting only the rows that have class name as either face with mask or face no mask. Then finally, once this data frame is filtered out, we're resetting the index and we're dropping the index after it has been resetted. Then with this line of code, we're sorting the values in the trained data frame by the column name. So if I run all of these lines of code, we have now filtered the dataset as well as sorted the values in the dataset by the name column. Now let us look at the unique labels that are in the class name column. So if I run this, you can see that we have face no mask and face with mask remaining. Let us also look at the first 5 rows of the trained dataset by calling the head method off of it. Here you can see that we have images with class names as face no mask or face with mask. Let us also look at the distribution of these labels in order to understand how many rows are there with class name as face with mask or face no mask. So for this, I'm setting the x-axis values as face with mask and face no mask, since that is what we want to look at. And for the y-axis values, I'm selecting the class name column from the trained data frame. So this is another way to do the selection, and I just wanted to show it over here. Then we're calling the value counts method, which gives us the value counts of all of the elements inside of the class name column and the counts. So once we get the y-axis values as the counts of the labels, we can plot a bar plot. For that, I'm using the bar method from the pyplot module of matplotlib, and I'm passing in the x-axis val and the y-axis val as our parameters. So if I run this, you can see that we now have a plot where it shows that face with mask has above 4000 different samples in our dataset, whereas face no mask has about 1500 different samples. We can see these classes are imbalanced right now, but that is okay for this project. In a real world project, you'd want to balance these datasets out or use an algorithm that can work with these imbalances. Now that we're done with looking at the train.csv file, let us look at the folder which is medical mask, medical mask, medical mask and images. So here I'm writing out the images file path and I'm assigning it to a variable over here. Then I'm printing it out. So if I run this, you can see that our new image file path is this one. Now let us also look at how many images are in this file path. So for that, from the OS library, I'm calling the list_dir method, which is list out the directories, and I'm passing in the file path that we had created above as our file path. So this returns an array with all of the file names in the directory, and I'm storing it in the variable image file names, and finally I'm printing the length or the count of these image file names by calling the len method and passing in the image file names array as a parameter. So if I run this, we can see that we have a total of 6024 images. And remember, these images have not been filtered out for face with mask and face with no mask. These are just the images that we had in the dataset when we downloaded it. So for filtering them out, we can use the train.csv file to help us with the task. But before that, let us see how the image file names look like, and I'm selecting the first 5 rows from the array. So if I run this, you can see the images file names are as follows. Again, we'll not be using all 6024 images, and we'll be only using the images that have the name in the train dataset. And as you can see, our name starts from 1801.jpg, not 0001.jpg. So let's plot a sample image from the filtered train dataset in order to understand how to load in images based off of it. For that, I'm selecting the first index from the train data frame and I'm selecting the column which is this value. So once this is done, I'm assigning it to the variable sample image name, and I'm concatenating or adding 2 strings together to get our complete file path, which is stored in the variable sample image file path. So if I print this out, you can see that we have our complete file path over here. Next, let us read in this image as an array. So we're reading the 1801.jpg image by using the imread method from matplotlib's pyplot module, and we're passing in the parameter as our file path, so this one over here. And once this image has been read in as an array, we're storing it in the variable img. So I'll run this, and if we want to look what img looks like, you can see that it's just an array of pixels. So as you know, in computers, pixels are stored in the format of arrays. So if I see the shape of this array, you can see that it's a 3-dimensional array. That means we have 3 different dimensions, which is the color channels, red, green and blue. And for each dimension, we have 1385 by 1386 pixels. These values of pixels may differ from one image to another in the dataset. But for now, since we already have a sample image, let's work with it. I'll remove this cell for now. Next, let us plot the image using matplotlib.pyplot. So here I'm creating a figure and a subplot axis using the subplots method from the pyplot module. This returns back a tuple of figure and axis objects, and using the axis object, I'm calling the imshow method off of it and passing in the image, which is our image array. So if I run this, here's our plot. Great, we have successfully loaded an image as a NumPy array as well as plotted it out. Let us also plot the bounding box on top of the image as well. So for this, we need to fetch the bounding boxes for the image using the train.csv file. So here, I'm first selecting the name column from the train data frame, and I'm selecting the images that are equal to the sample image name, which was 1801.jpg. Then again, I'm filtering the rows where only this sample image name is present, and I'm assigning this filtered out data frame to the variable cell_df. Then for the bounding box, we're selecting these columns off of the cell_df data frame and we're converting it to values and then to a list. So once we have a list of coordinates for the image, we are assigning it to the variable bboxes and I'm printing it out. So let me run all of this code and show you what bboxes look like. So we have a list of lists containing the bounding boxes in the image. So there is only one face in this image, so there's only one bounding box over here, but in reality there could be multiple faces in any of the image and there could be multiple bounding boxes. So in that case there would be multiple lists inside of this outer list. Now let's plot the bounding box using the rectangle patch from matplotlib.patches module. The rectangle patches method requires 3 major parameters to create a rectangle defined by an anchor point xy and its width and height. So the 3 parameters are the starting xy coordinate, which is given by x1, x2, then width of the rectangle, which is given by y1 minus x1, and height of the rectangle, which is given by y2 minus x2. Here you can see a representation of what x1 and x2 and y1 and y2 look like in an actual image. So our starting xy coordinate is x1 and x2, and for the width of the rectangle we just minus y1 minus x1, so we're subtracting the x-axis coordinates that gives us the width, and for the height of the rectangle we're subtracting y2 minus x2, so that gives us the height of the image. By the way, the reason we have these coordinates as follows is because if you look in this figure, you can see that the y-axis values has its starting 0 value at the top instead of the bottom. So that's the reason our x1 and x2 is at the top. So let's plot this bounding box out. For this, I'm again calling the subplots method and getting the figure and the axis object. Then I'm calling the IamShow method from the axis object and passing on our image array. Now this is something different. We're plotting the bounding boxes over here. Remember that one image can have multiple bounding boxes. So we're iterating through the list that we had created called bboxes, and for each bounding box we're performing the following actions. So the box values are x1, x2, y1, y2. So if you remember, we have 4 different values which are x1, x2, y1, y2. Next, we're just calculating the parameters that we want to pass to the rectangle patches. So our starting coordinate xy is x1, x2, our width of the box is y1 minus x1, our height of the box is y2 minus x2. Then we're calling the rectangle method off of the patches module of matplotlib and we're passing in the parameters xy, which is our starting coordinate, the width that we want the rectangle to be of, the height that we want the rectangle to be of length, and the line width, which we are setting it manually to 2. You can set it to any number that you want. We're setting the color of the edges as R for the rectangle patch, and for the face color we're removing it so it's none over here. So once this rectangle patch has been made, we're adding the patch onto our axis object by using the add patch method and passing in the patch. Again, we're creating the rectangular patches for all of the bounding boxes we have. So if an image has multiple bounding boxes for faces, then we're plotting different rectangles on top of the same image. So if I run all of these lines of code, you can see that our bounding box has been plotted out. Great, now that we have had a look at both our train.csv file as well as the images folder, we can start creating the training data. So before we move forward with creating a training dataset, there are some things to consider. First, the resolution, which is the width times height of images in the training dataset, is relatively high. For example, if an image is of size 1280,720, then the number of pixels we would be feeding in the convolutional neural network, which is our model, will be 1280 into 720 equals to 921,600 pixels. Training a model using this many pixels will take a lot of time. Second, the images have a color depth of 3, that is red, green and blue. So the total number of pixels would actually be 1280 into 720 into 3. That's about 2 million pixels. So that's way high than what we have time for right now. So since this is just a practice project and we'd want to build an average performing model quickly, we'll do the following manipulations to decrease our number of features. We'll convert the color depth of the image to 1 by reading in the images as a grayscale image. We'll crop out the region covered by the bounding box in each image, and finally we'll resize the image to be of a size 50 into 50. So one image will have a total number of pixels as 50 into 50 into 1. That's not quite a lot. So let's work on that. All of this code over here does that for us. So I'll go one by one and I'll explain what is happening in each line. First, I'm setting the image size variable as 50 since we want to resize the image to 50 by 50 later down the line. Then I'm initializing an empty Python list and I'm storing it in the variable data. So in this list, we'll be appending the actual image arrays along with their class name so that we can have them together. Next, I'm iterating through each of the rows of the dataset that we have created so far, which is our filtered trained data frame where we only have the labels as face with mask and face no mask for each of the rows. So the iter rows method iterates through the data frame one by one and it gives us the index and the row for each of the data frame. So once inside of this loop, so let's say we're in the first row, we get the name, the x1, x2, y1, y2 and the class name, which were our actual column values. So we just need to call row.values to get the values for the first row for all of these variables. So we're just unpacking these values in these variables over here. Now we need the full file path to read in the image as well. So for that, images file path is our long folder name and name is the actual name that we have retrieved from the row. So once this image file path or our complete image file path has been created, we store it in the variable full file path. After that, we use the imread method off of the CV2 library, which is OpenCV, and we pass in the parameter as our file path as well as specify that we want to read in this image as a grayscale image by calling in the imread_grayscale attribute from CV2. So once the image has been read in as a grayscale image, we're storing it in the variable img_array. Remember, the next step was to crop the image. So for that, we're just cropping the image by selecting from x2 to y2 for our rows and x1 to y1 for our columns of the image pixels. So once that is done, we get the crop image back, and finally we're resizing the image using the resize method and we're passing in the crop image array as our parameter as well as the image size, which is 50 by 50 for resizing. So once this image has been resized, we get back new_image_array. And finally, once everything is done, so next we append these values to the data list that we had initialized earlier. So here we're appending the image array, which is our cropped and resized grayscale image array, along with the class name as a single list. So to summarize, we're iterating through each of the rows of our data frame, we're selecting the row values, we're creating the full file path, we're reading in an image as a grayscale image, we're cropping the image using the bounding box coordinates, we're resizing the image to the size 50, 50, and finally we're appending the values of the cropped image as well as the class name in the data list. So I'll run all of these lines of code in order to actually create our training data set. So I'll run this and this will take some time, so please wait it out on your end. For now, I'll just skip to the portion where this loop has been completed. And that's done. So we've created our training data set. Now let us see what is the content inside of the data variable we have. So for that, let me just write data over here. So you can see we have an array followed by the class name. So for each bounding box in an image, we have an array of pixels as well as the class name associated with that bounding box. So if I write data 0 over here, you can see that we get the first bounding box along with the class name. And if I write 0 again, we get the pixel values for the bounding box in the form of a NumPy array. So let us plot this array out and let's see what it looks like now. So for that, I'm calling the IAmShow method from the PLT library, and I'm passing in the parameter as data00, which is our array, and I'm setting the color map to gray because this is a grayscale image. So if I run this, you can see that now we have a cropped and a resized image. That's why it's pixelated for each of the images that we have read in our training data set. Let's look at another image. So I'll write data10, and this is another image, and this is another image. So now we have our training data set ready. I hope you can see the results of what we have done so far in this single image itself. I'll just revert this back to what it was. Okay, now let us separate out the independent variables, which are our NumPy array values and our labels. So for that, we'll be calling x as our independent variables, y for our dependent variable, which is the label. So for each array in our data variable, we're getting the features, which is the NumPy array pixels, and the labels, which is the class name, and we're just appending it to the variable x and to the variable y. So the variable x has the NumPy array and y has the class name. So if I run this, the appending is done. Now we need to reshape the image array to a proper format for our independent variables. So if we look at any one of our independent variables, the shape is 50 by 50. But when passing the independent variable x to the convolutional neural network, we need to follow the following format. That is the number of images, comma, the height and width of the image, and the color depth. So since x is a list, I'm converting it into a NumPy array, and then I'm reshaping it using the reshape method by passing in the values as -1, that is we want to select all of the images, we want the image size to be 50, 50 and the color depth to be 1. So if I run all of this after reassigning this reshaped array to x, and if we look at the shape, we see that there are 5749 images with the width and height as 50, 50 and 1 as the color depth. Next, let's normalize the images. So if we look at the minimum and the maximum value of one particular image in our training data set, we can see that the minimum value is 4 and the maximum value is 253. So a pixel is represented within the range of 0 to 255 in the case of an image, and since this is a grayscale image, we only have that range to work with. So instead of using values 0 and 255 in our mathematical equations, we would want to have a smaller representation of this range. So for that, we're normalizing the range between 0 and 1. So using the normalize method from the Keras library, and I'm passing in our array and our axis is 1. So once this has been normalized, we're reassigning it to the variable x. So if I run this, the normalization has been done. Now if we look at the minimum and maximum value, we can see that the values are in the range of 0 to 1. Next, let us label encode the target y. So if I print the first 5 values of y, you can see all of these are strings. So we can label encode them. So for that, I'm instantiating a label encoder object and assigning it to the variable label. Then I'm calling the fit transform method off of the label encoder, and I'm passing in as parameter the class values or the dependent variable y. Then we're reassigning the label encoded values to the variable y. So if I run this and let's print out the first 5 dependent variables, we see that 0 is associated with the class FaceNoMask and 1 is associated with the class FaceWithMask. And one final thing that we have to do in order to wrap up this part of creating a training dataset is to convert these labels to categorical variables. So for that, I'm calling the to_categorical method, and I'm passing in the parameter as this label encoded dependent variable. So once this has been converted to a categorical variable, I'm reassigning it to the variable y. So if I run this, and if we print out y, that is the first 5 rows, we see 1 0 0 1 0 1 0 1 0 1. So after converting to categorical variable, if we get 1 0, the class label is FaceNoMask, and if we have 0, 1, the class label is FaceWithMask. So this is FaceNoMask and all the rest 4 are FaceWithMask as we had seen before. So that wraps up our first part on creating a training dataset. As a summary, we looked at the train.csv file, we looked at the images in the images folder, we filtered out the train.csv file with class names that we are concerned with, then we plotted out and saw what kind of images are in the image folder. We created a training dataset by reading in the image as a grayscale image, we cropped it and resized it as well, and finally, we did some data preprocessing on the independent variable as well as the dependent variable to train our convolutional neural network. So in the next part, we'll be learning how to train an image classification model, that is a convolutional neural network in this case.